This is Code Dive 2021. Let's continue with Adam Pietrzyk. Adam is an application engineer at SciTech Software, Oprogramowanie Naukowo-Techniczne in Polish, a MathWorks authorized reseller for Poland. At MATLAB and Simulink, he is responsible for simulation, physical modeling, C code verification, and model-based design. He graduated from the AGH University of Science and Technology in Cracow with a degree in electrical engineering. So, implementing innovations in a safe and secure way, Adam, the floor is yours.
Hello, I'm Adam Pietrzyk. I work as an application engineer at ONT, MathWorks authorized reseller in Poland. Today I would like to speak about implementing innovation in a safe and secure way and how automatic code analysis can help you with that. Here is the agenda of my presentation. It's not much, only 2 main points. So, firstly, I would like to speak about dynamic testing and why it's not enough. Let's start with a number. What do you think does this number means? By the way, it's not related to coronavirus. This big number, $7.5 billion, is the cost of the crashed Ariane 5 rocket. Here was an overflow in inertial reference system when converting the sideways velocity of the rocket from 64-bit float to a 16-bit signed integer. The onboard computer misinterpreted a diagnostic message from the inertial reference system as real flight data. Believing the rocket is veering off course, it commands an immediate course correction of 30 degrees per second. 2 seconds later, with the boosters about to be ripped from the rocket by aerodynamic forces, an automatic self-destruct is triggered and Ariane 5 becomes the most expensive firework. We have plenty of other examples in the industry as well. There are plenty of other examples in the industry, like in automotive. The worst case situation for OEMs in the automotive industry is to see new reports about recalls. They are frequently in the news. It means that cars and other safety critical devices need to be recalled from the vendor. Recalls are expensive and damage the brand. With growing software content in cars, it is further damaging when software bugs cause recalls as shown in these news articles for Chrysler, Daimler, and Toyota. Let's look at another example, more related to security. Maybe you have heard about Jeep's hack attack a couple of years ago. 2 guys, Charlie and Chris, remotely gained unhindered access to almost all of the vehicle's systems via internal vehicle network. As you can see, for example, they present funny photos on the infotainment screen. Let's look at the video. It isn't an autonomous vehicle. It is really a hack attack. As you can see, Charlie and Chris are able to accelerate, brake, steer, and lock the doors. These kind of challenges are very frequent these days in the industries and need to be addressed in a certain way. One thing is testing a lot. But the problem is that tests and code reviews can never be exhaustive. So you can test all for bug, but you can only show the presence of bugs, but never their absence. That is actually the biggest problem for testing. Testing is perfectly fine for functional tests. That means if you have functional requirements, you can address them very well through testing, but some kinds of software bugs like division by zero, overflows, array access out of bounds, this kind of systematic issues cannot easily be found with dynamic testing, with software execution. Here is, for instance, another example. This is, by the way, a real example from one of the customers who is really using Polyspace. It's a static code analysis tool. And he mentioned, okay, the tool says that we have a problem. We do not enter the if condition. And we have division by 0 here. What did I do wrong? Why Polyspace shows me this problem? Because it's obviously not the case. So we have if a is less than 0 and a is initialized with -1, it's obviously less than 0. So why we do not enter the if condition and assign -1 to the divisor? And then we have a return value -100, not division by 0. I said, okay, what we can do is write the code and debug. This is what I actually did. Here you can see my Eclipse environment. So I write the code example with little main function around, just to be sure that this kind of defect is really there. The compiler there was a GCC compiler, so it's really standard. Now you can see I entered the code from my main function. I enter function, can you find a bug? And I start going step by step through the code. And what you can see, I just skip over the if condition. So also the debugging shows me, okay, there is something wrong in this code. And you can see in the variable trace that divisor is 0. This kind of defects can be easily introduced while programming, and it's sometimes very difficult to find this kind of defects in dynamic testing. What we can do here is to integrate Polyspace, which is a static code analysis tool, inside the Eclipse environment. So what we have here is a plugin for Eclipse, and you can use the static code analysis in the same way executed directly on the code you have just written. Here we have some Polyspace settings. Actually, what you can do here is you can choose what kind of coding standards you want to apply, for instance, a MISRA. What kind of checks you like to apply. You can see plenty of numerical checks, like division by 0, overflows. You can see security issues, static memory things. I will not go more into details. You can choose which kind of engine you like to use, the Bugfinder or Code Prover engine. So we have different static code analysis tools. I will show you the difference later. And finally, you can run an analysis on your code. You can choose the scope as well. So just run a static analysis on a certain files, or you can run analysis on whole integration, including the main function and all of this. Finally, we got some annotations, some informations. All the findings that we have, you can trace here in the result list. But you can also see on the right side some detailed information, like if condition always evaluates to false, that's we already know with the dead code. We also already know about division by 0 here. So what is really interesting for us, it's the root of cause of our defect, and this is here. A sign change from integer, that means there is conversion overflow. This is a specific thing in C language that you have implicit casting of types, and in this case we have unsigned type on the right side, which means that signed type on the left side will automatically be converted to unsigned, which means that -1 get very large value. So here we got an overflow. That's very nasty effect of C language and needs to be found during coding because it can be easily introduced even by experienced developer. That's one effect that you can achieve by running static code analysis exactly from your IDE. So you can use the static code analysis tool early on some piece of code you just wrote, and as you saw, it can significantly reduce time spent on investigating unintended behavior of your algorithm. So as you reduce time spent on finding bugs, you could focus more on implementing innovations, algorithms, and so on. Let's see other benefits of using modern static code analysis tools like Polyspace. So, how does static code analysis really help you? As I mentioned before, it finds bugs and security vulnerabilities early on. You can check for coding rules conformance like MISRA, CERT-C. There are plenty of different others like authorized C++14, or you can create your own. It provides you metrics you may need like cyclomatic complexity and so on. And this is really unique, it proves the existence or absence of runtime errors. I will go into detail and demos later to understand what it really means, but finding and proving the absence of bugs, it's a completely different topic. Another thing is that you can indicate when you reach a certain quality level. It's probably more interesting for companies than single devs, but static code analysis tool can help you to achieve software quality objectives, trace it in a larger team. I will not go into details in these presentations. And the last but not least, it can help you with code certification. Standards usually have a lot of tables full of requirements, what you need to do in the development process. There are some requirements like using a static code analysis tool or doing dynamic analysis or doing data flow control analysis using formal methods. These kinds of requirements can be found in functional safety standards a lot. And the question is how to apply to those requirements. And the static code analysis tool can really help you. Okay, that's briefly how static code analysis can help you and why dynamic testing is not enough. Now let's go more into details. How does formal code analysis work? And in other words, can you rely on your software? Take a look at this code. It's C code. It's not written very well. There are non-initialized variables. Later we initialize some of them, but we are not sure if all of them are initialized. There are some plus operators which can overflow. We have if statement. Maybe we can't enter there, or maybe it's useless. We don't know it yet. We have a while loop. It could be infinite, and there is division operator. And if x equals y, there is division by 0. We have plenty of problems there. It's pretty challenging to find all of them in code reviews, but I think it's an impossible task. Code reviews are very important, but we need to have reviews on some data. This data can be some test status, coverage reports, or static code analysis output, but not plain code. This is really a nightmare to do a review on a plain code. Let's consider 21st line. Could there be a bug here? Let's take a look more into details. What are potential runtime errors in this line? Variables x and y may not be initialized. There could be an overflow on subtraction. And if x equals y, there will be a division by 0. So if we consider all potential function entries, how to prove that runtime errors do not exist. Okay, one of the possible ways is to test all possible inputs. Let's make the assumption that both function entries are assigned int 32. The result is that we have 4.61 times 10 to power 18 of test cases. The execution of 4 million test cases took on my host machine slightly over 9 seconds. That means exhaustive testing will take 339,000 years. As you can see, exhaustive testing in this situation is impossible. You may have a more powerful machine or some cloud resources, but still exhaustive testing takes too much time. So if exhaustive testing is impossible, we need another approach. Let's take a look at how static code analyses work. In this example, I have this piece of code inside my Polyspace. I'm launching static code analysis. In this case, it's Code Prover. As you can see, I got a pie chart which shows me 33 green checks. On the left side, you can see all the results, which are all proven that there is no defect. There is no mathematical possibility to occur runtime error. You can dive to mathematics behind, you can examine values ranges. This kind of static analysis is called a formal method-based static analysis, which really proves each and every operation is mathematically sound, which means whenever you have a green, you can rely on color. You can rely on that there is no input which can cause defect. But how does it work with the proof of freedom from errors? Polyspace automatically verifies all possible executions a program can go through. The goal is the formal proof that the operations of a program are correct in the sense of the semantics of the programming language. In example, cannot cause runtime errors. The only requirement for this is the compilable program code, which must be available in the supported programming language like C or C++. Moreover, Polyspace helps to discover the sign even before the program is executed. A mathematical method called abstract interpretation is used to verify the program code. If the correctness of an operation can be proven, it is marked in green. This means that the correctness has been proven here. Red means that an error will occur every time this operation is performed. Gray, that for example a certain branch can never be executed. And operations are marked in orange that could not be clearly proven to be correct or incorrect by the abstraction mentioned. It is important that every operation of a program that could cause a runtime error is checked. The properties can be proven by the fact that Polyspace remembers the value ranges of operands. Take a look at how does the formal analysis works. Let's consider another example. This time we have pseudocode. Firstly, we read some value for a. It could be from file or other variable. It doesn't matter. We don't know what exact value has a, but we know that it's int type. And we know the range of int type, so a could be any value from minimum int to maximum int. Next line, we increase value a by 2. Possible values for a changes, and now it's from minimum int plus 2 to maximum int. The plus operator is marked as orange because there could be overflow when read A equals to maximum int or maximum int minus 1. The upper branch of if condition is evaluated only if A is greater or equal to 3. So far, so good. An underflow can be rolled out, but a division by 0 not yet, because if A equals 8 during program execution, we can be witness of a program crash. The usual procedure at this point would be for the developer, for example, to gradually increase the robustness of a function, taking into account that functional specifications, for example, by adjusting the if condition. As we modified if condition, now there is no possibility to occur division by 0. Using formal analysis, we don't need to write test cases or even execute code to prove the absence of runtime errors. Let's move back to the example with division by difference of x and y. We can plot it. You can see x and y on the axis, and each cross is potential pair of x and y values. The red line is the error case. That means for static analysis tools, which is more based on pattern matching, that it must flag it as a potential risk. In this example, it leads to a false positive. If you look more into detail, there is no real occurrence of a bug because the real crosses are not on the error line. It's one example of how Polyspace formal method works. It divides value ranges more in clusters. That is why it calls Polyspace. It's not just saying that values of x are from 3 to 7. It can have really multiple values ranges to support more accurate estimates of state spaces where variables are really in. This helps to prove that the error line does not cross any of the state spaces. So you will get fewer false positives. You are really able to make more of your code green, which is really helpful because you can focus on remaining part of your project, not on daily reviews. Now you know how formal code analysis works. Maybe you remember the question from the agenda: can you rely on your software? Let's try to answer it before we go to the summary. Maybe you think you don't need tools like Polyspace because you got well-written requirements, lots of unit and integrating tests, and you are almost 100% sure that runtime error is not possible and you found all possible security vulnerabilities and you fix them. But is it enough? Okay, in this integration, maybe yes, maybe it is enough, but what in the future integrations? When you want to reuse some piece of your code, can you still rely on that? Well, maybe you remember Ariane 5 rocket from the beginning of the presentation. The rocket's makers thought they could rely on the code written for the Ariane 4 rocket. The crash led to a public inquiry, and throughout the destruction of the rocket's payload, delayed scientific research into working on Earth's magnetosphere for almost 4 years. Let's go to the last part, and I will summarize goals and benefits of static code analysis. Polyspace can be applied for handwritten and auto-generated code. It supports C, C++, Ada code, and it's based on a formal method which is based on semantic analysis, what I already mentioned. Formal method inside is abstract interpretation, so you can Google that. There is a lot of information on what abstract interpretation really means. There is a lot of number crunching in between, so that also turns out that static code analysis tools take a little bit more time to compute your code than very simple ones, for instance, compilers, which usually also have static analysis inside. GCC compiler, for instance, also has some checks. You can apply them, but they are usually not based on abstract interpretation or deep semantic analysis. It's a more pattern matching approach, which is of course also very helpful, but it leads to a lot of mistakes which cannot be detected or can be overseen. And finally, the goal of the analysis is to find runtime errors like division by zero, overflows, to complying with certain standards, coding standards like MISRA, for example, to provide code metrics, and to prove absence of runtime errors. Polyspace Tools divide into two different engines. The first one and the basic entry port is BugFinder. BugFinder can help you with code metrics, finding complexity metrics, stack usage, project file function metrics, and a whole set of HIS metrics. It provides you a lot of different check categories for coding standard and coding rules like MISRA, AutoSAR, CertC, CWE. For instance, MISRA focused on coding security standard. It was born in the automotive industry as collaborative effort, vehicle manufacturers and component suppliers. MISRA has gained acceptance in other markets such as aerospace, biomedical, embedded, IoT, and industrial control systems as well. And it also helps you to find a lot of different checks in terms of numerical issues like division by zero, overflows, static memory issues, arrays out of bounds, programming issues, concurrency issues. I will not go deeper into details. If you want to know more, you can find it in documentation, or I can provide you a whole set of defects and vulnerabilities checks. Starting to use BugFinder at the beginning of the development process helps you to find possible issues. You can focus more on innovations rather than code reviews, because Polyspace findings can be valuable input for code reviews, which will be shorter. The idea of BugFinder is to give you a tool that is easy to apply to maintain high-quality code, which is secure and safe. Also complied with the different standards, and this tool can be really applied quite fast on a large code basis. It's really simple to use, gives you very precise information in terms of less false positives, less false warnings, but it may also oversee defects, so it's not complete in a way that it really proves the absence of runtime error. And this is a part of Code Prover. Whenever you heard about Polyspace some years ago, it usually spoke about Code Prover. So the technology that Polyspace was some years ago, it's really what you can find now in Code Prover. The BugFinder has been developed later in 2013, so it was also a long time, but Code Prover technology exists much longer. Code Prover is pretty unique. You don't find it in many code analysis tools. It can really prove the absence of runtime errors. Code is colored by green as we see before. It can apply these kinds of check on a subset of critical objectives like division by zero, overflows, and so on. With Code Prover, you can really prove your code for the absence of runtime errors in each possible and in any different integration scenarios, which you don't have in front of you, but which are potentially possible. And it gives you fully trusted components. It's important for platform code, for libraries, for safety critical code. It also helps you to find potential issues which may not be available in your current integration, but maybe in integration you never thought about. Maybe you have different parameters set later on, or you want to reuse your code in another device like a new racket. So there are scenarios where Code Prover can really help you. Thanks for your time, for your attention, and have a nice remaining part of the day.
Thank you very much indeed. This was Adam Pietrzyk talking about safe and secure innovations. Just a quick reminder, our challenge, a virtual escape room, will start on our website soon after the conference, and we have some prizes. So a laptop for the winner, a monitor for the second place, and 3 sets of wireless headphones for 3 people, those who come in third. Don't miss it.